In this video we're going to talk about vector combinations. One of the greatest benefits of drawing the vectors is to visually represent multiple vector quantities that are acting together. The simplest one we'll start with here is simply to find the total displacement of an object over a series of movements. So we'll go ahead and start with a displacement in our example here of something that goes 6 meters to the east. So we need a scale, right? So don't forget, we always have to identify what we're going to do here. So let's just do 1 centimeter equals 1 meter, and let's just stay with the standard up on our paper is north. So we have a 6 meter displacement we want to represent, and so we're going to have to draw it 6 centimeters. And it's going to the east, so that's east, and that's 6 centimeters. That represents the 6 meter east vector. So you can imagine it's like a person, right? A student at school walking along in the hallway, those 6 meters to the east. And let's say they stop after the 6 meters, so they stop here. Maybe talk to a friend, something like that, you know, see $1 on the floor, whatever it might be. And then they continue on, and the next displacement go 4 meters continuing to the east. So our next vector here is going to be 4 centimeters long, and so we just continue where we left off. Draw out 4 centimeters. And that represents our displacement of 4 meters to the east. So this now at this point leads us to our first rule of vector combination. So rule number 1. Line up all vectors tip to tail. So here we have the tip of the first vector, tip, and here we have the tail of the next vector. So always line them up tip to tail. Now the example we use, it kind of made sense. If you're walking along and you stop here and you start back up again, you're going to start right here and continue on, in this case, in the direction that you went. So always line up your vectors tip to tail. Remember in doing that to keep the direction, right? So as you line them up, since this was supposed to be going east, it still goes east from this point. So you know where you started from, and it goes in that direction because that represents the actual displacement that's given to you there. So just looking at it, we can say, well, you know, the person walking along here went a total of 10 meters to the east. This 10 meters to the east then is the result of this entire trip. So rule number 2 that we have for vector combination is what's known as the resultant vector. Resultant vector. Always draw the resultant vector from start to finish. So we started here, went through the whole trip, and finished here. So our resultant vector basically would start and go along like so. No, it didn't happen up above it, but it's easier to see it when we draw it up above it here in this case, right along instead of directly over the actual arrows that have been drawn before. And so that, if we measured that line, would be 10 centimeters. That 10 centimeters then represents 10 meters according to our scale at 1 centimeters equals 1 meter. Now let's have our person here continue this trip let's have a displacement of 7 meters west. So let's have them go 7 meters west. So again, our scale, west is back to the left. So we have our person here, and we'll start them right where they were. Again, line up all vectors tip to tail. So since we finished right here after this vector, the 4 meter vector, you're going to start and go to the west. So you have to go keep the direction, go all the way back to the west, about 7 centimeters on our scale, or 7 meters in the real world, like that, and we have 7 centimeters there. So now again, we're lining them up tip to tail. So we had the first vector, stopped, continue the motion here, stopped, continue the motion, went back this way. So our 7 meter west vector has to be pointing back to the left, which is why it heads back this way. Again, it really does trace over it, right? If we could put it along here, is really where it's going. That's kind of hard to see over the other vectors there. So I always draw it a little bit above it just to kind of see what's going on there. Now, the next thing we have to do here is find that total resultant vector, which again is going to be drawn from start to finish. And so we started here, and this time we finish now for the total of all 3 vectors here. So we'll start and draw our resultant vector like so. And since we went from left to right, then we draw the arrow in that direction. Alright, so essentially all this out here just kind of canceled out, right? In terms of displacement, it does really no effect of what you did here because we just walked back the other direction. And so our resultant ends up being, if you measure this out, 3 centimeters or 3 meters according to our scale. So we have a total resultant displacement of 3 meters to the east. We have 2 vectors, displacements going in the same direction. We combine those together to find that resultant. And then we had vectors going in opposite directions. Again, in both cases we line them up tip to tail, and then we find our resultant by lining them up start to finish. So the next example we're going to look at will be when we have 2 vectors that are at right angles to each other. So here we have 2 vectors, 20 meters to the north and 15 meters to the west. I made a scale, 1 centimeter is 5 meters, and up is still going to be north. So we want to do the vector combinations. We're going to line up the vectors tip to tail. So we'll start by drawing the first one. Since it's 20 meters, you need to look at what that would be according to our scale. So 20 meters divided by 5 meters per centimeter. That gives us 4 centimeters. So we're going to draw our vector north, about 4 centimeters. Alright, if you do this with your ruler, right, you'll be able to measure everything exactly, a little bit straighter than what I've got here. And then the second vector now is 15 meters to the west. So the same kind of idea, we have 15 meters divided by our 5 meters per centimeter. That gives me 3 centimeters. So again, tip to tail, so we started here, moved up this way, 20 meters. We're going to start here now and go to the west, 15 meters, which is 3 centimeters on our scale. So 3 centimeters, like so. So now we have these 2 vectors at right angles to each other here. So again, the resultant, still the same rule, right? We lined up our vectors tip to tail. Didn't change any directions. We kept the north going north. We started here. We drew the one that went to the west off to the west. And so now our resultant has to go from start to finish. So we have the start here, and we have the finish here. So when we draw it, draw your vector like that, and since you went this direction, don't even pick up the pen, just go ahead and draw the arrow on there, start to finish. Right. This does not continue the circuit, You don't start here, go up here, go over there, and then come on back down. The green arrow here, our resultant, is simply what you would see or what would happen if you didn't go in these two separate directions. If you just did one trip, instead of walking to the north and to the west, you could walk up this way to the northwest. Alright, now we need to figure out the actual displacement, the actual magnitude. So we know the direction. Alright, so if we want to find the total displacement here, we know the direction is northwest, but how far is it? How many meters is that? We need to know how many meters it is. The easiest thing to do, if you've drawn this out to scale, if you used your ruler, drew an actual 4 centimeters and 3 centimeters, just measure this vector right here. And when you measure it, you should get 5 centimeters. And so on our scale, each centimeter is 5 meters, we simply get 25 meters northwest. So that's our total displacement. The other way to find the total displacement when you're talking about vectors at right angles to each other is to look at this as a right triangle. You have a right triangle, you have side A, side B, and side C. So we can use the Pythagorean theorem, a squared plus b squared equals c squared, and solve for that value. So our A value was 4 centimeters. So we have 4 squared plus our 3 centimeters, 3 squared equals what our c squared. So I've got 16 plus 9 equals my c squared. So 25 equals c squared. Now to unsquare it, we just take the square root of both sides. So c equals the square root of 25, which is 5. And I've left out all the units and everything, but these were centimeters, and then centimeters squared. And then we take the square root of that ends with centimeters again. So we get 5 centimeters for that length, which is what you should have measured up here. Now again, put it back into the scale. 5 centimeters then gives us again 25 meters, and our direction being northwest. So as you can see, we can take vectors that go in the same direction, vectors that go in opposite directions, and specifically we're looking at vectors that are at right angles to each other. You can do any angles, but these are the 3 main ones that we're going to be focusing on. And so that's how we do our vector combinations.